Okay, so there at the top, we've got just a couple blanks to fill in. It says, if the values of a function are the same for each given interval of the domain, the function is said to be periodic. And the length of the interval that is repeated is called the period. Okay, so what we're going to do here is we are going to graph sine and cosine. So just to help set it up here, on your x-axis here, I have tick marks here. This is going to be 0, and we're going to go from 0 to 2 pi here. So this is split into 4 sections. So if I take 2 pi and divide it by 4, that gives me pi over 2 right here. So that would mean the next tick mark would be 2 pi over 2, and then 3 pi over 2, and I could put 4 pi over 2 here, but that's equal to 2 pi. 2 pi over 2, what's it equal to? Not 360. 180, which is just pi, right? So let's change that actually and make it a pi. Right there. So you can see in your table here, that's the numbers you have here, 0, pi over 2, pi, 3 pi over 2, 2 pi. It seems, when you see it written like that, it kind of seems like just crazy numbers, but this is pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, right? It's just going by increments of pi over 2. And so you'll also have negative pi over 2, pi, negative pi, negative 3 pi over 2, and negative 2 pi over here. And we're going to put a 1 right here. Negative 1 right here on the y-axis. So what I want you to do is I want you to look at your unit circle and fill in this chart here for me. So you're going to find sine of 0. Somebody tell me just real quick, what is sine of 0? I don't think so. 0. Okay, so sine of 0 is 0. Then you're going to find sine of pi over 2. Pi, 3 pi over 2, 2 pi. Fill in this chart, and then you are going to graph those points on this graph. So, you know, like that first point right there would be at 0, 0. So, or that 1 point that I have right there. So, I want you to do that for me. I'm going to cut my screen off so you can't see what I'm doing. I'm going to do it as well. And then if you finish sine, you can go do the same thing for cosine. You are putting in the sine of that angle. So not degrees, but sine of that angle. So like sine of 0, you're looking at the coordinates at that point, which is 1, 0, and you'll be finding sine, which is the y coordinate. So that's why sine of 0 is 0. Y coordinate, yes. finish sine, go ahead and do cosine there on the bottom. We'll do that. You can do it. Okay, I think most people at least have sine done. Alright, so let's look at what we've got up here for sine. So you should get 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0 here. And when you graph it, it's going to look like those purple dots that I have up there. And so some of you just have dots. Some of you drew in your lines. Okay? However, some of you drew in your lines incorrectly. It is not a zigzag. Okay, so if I had asked you to graph like some intermediate points, so like pi over, like if I think about here, pi over 6, if we're thinking about the unit circle, would be right here. It is 1/2. So it would be like right here. Then pi over 3 is square root of 3 over 2, which is like 0.8 something. So it would be more like right here. So it does not go like a zigzag, like a straight zigzag. Whenever you draw these in, we're not going to graph those intermediate points necessarily. We're just going to draw it as a nice curve here. So if yours is zigzagged, go back and make it curve a little bit here. Or if you just had points, draw that line right there. And so if we graph this, it's just going to keep going up and down like a wave right here, which makes sense because every time you go around that unit circle, you just keep getting the same numbers over and over and over again, all right? So this can continue on forever. The period of this graph is the amount of distance on the x-axis it takes for this graph to start repeating itself. So, what is the period for this graph? When does the graph start to repeat itself? So, if we start at 0, how long does it take from 0 before it starts? To 2 pi, right? So, from 0 to 2 pi is a distance of 2 pi, which again makes sense because 2 pi is one full rotation. After one full rotation around that unit circle, it just keeps going, back around, same place. Domain for sine is all real numbers, or negative infinity to positive infinity. You can plug any number into sine, positive, negative, rational, irrational. Now, obviously, unit circle-wise, we've only got certain numbers we know how to deal with on the unit circle, but the calculator can take care of the rest of everything for us, right? You can plug any number in. What is our range here? -1 to +1. Should I use parentheses or brackets there? Brackets, because it does include 1 and -1, because it does actually equal those at times. Okay, questions? This graph needs to be something that you know well. I can guarantee you on Friday's quiz and whenever we test on Unit 6, which will be after Thanksgiving, there will be a question on both that quiz and the test that are going to just say which of these is the graph of sine. Or it might have the graph of sine and say which equation matches it. But it's just going to be plain sine. We're going to learn how to shift it up, down, left, right, flip it over, all of those things like we did with other graphs. But you have to know what sine looks like to be able to do any of that other stuff. One of the key components right here for sine is that it has a y-intercept at 0, 0. All right, we'll see that cosine looks almost the same, but it's not going to have that same y-intercept. Right? So we need to know what this looks like. All right, so your cosine graph, you should get 1, 0, -1, 0, 1, 0, -1, 0, 1. It's the same pattern, but right here the y-intercept ends up being at 1 for this one. So if I draw this in here, it also, of course, is curved. Like this. From a distance, sine and cosine look exactly the same, and more or less they almost are. But cosine's y-intercept is at 1. So it's just like we've taken sine and we've shifted it over a little bit, is what we have here. So what happens here is period is still 2 pi. Domain is still all real numbers, or negative infinity to infinity, and the range is still -1 to 1. Right, all of that stays the same. The y-intercept is really our difference there. Again, cosine, just like sine, you need to have that memorized. You need to know what that graph looks like. Now, what's so cool about this is so the reason we spend so much time on unit circle is to try to help you connect why triangles relate to these graphs. Because these graphs, we're going to look at where they apply to crazy situations that have nothing to do with triangles, right? So trig ends up showing up in all kinds of places in the world where you don't have triangles at all. So this is trying to help you connect. So the unit circle, because of the way the triangles work, creates this pattern that repeats over and over and over again, which creates this graph that goes up and down and up and down and up and down. And these types of graphs are really, really useful in a lot of situations, right? Anything that is repetitive can usually be modeled with a sine or cosine function. So if you think about things like temperatures throughout the year, it gets hotter in the summer, it gets colder in the winter, hotter in the summer, colder in the winter. So we could model that using a trig function, right? If you think of like the number of hours of daylight in the day, you know, long days in the summer, short days in the winter. There's all kinds of things it can be used for that have nothing to do with triangles. So it's kind of cool how it works out. So we're going to look at applications more on Thursday, tomorrow, Wednesday. Today, what we're mostly going to look at is transformations here. So how do we move these up, down, left, right, flip them over, stretch them out, all of those things that we've looked at before with other functions. So there is a second set of notes that's going to have this stuff. And usually in this section, I do a project that's really cool with ocean tides because they can be modeled using this, and we all pick up each location, look at the data, and there's all kinds of stuff that you can find. However, we just don't have time because we are out of time already. We're already going to have to skip matrices, so no projects this time for this because we're just barely getting by. All right, so let's look here. All right, so transformations to sine and cosine functions. The cool thing I think about transformations is transformations work the same no matter what function you start with. So if we need to move something up, we can put a +2 on the end and it'll move it up 2. If we want to move something to the right, we can put a -4 inside and it'll move it to the right 4. So all of that still applies with trig functions. It's going to have a few things that are different names when we're dealing with trig functions. So that is going to be something that's going to be a little different with this. So, all right, so translations, let's review this really quickly. So here, Josie, what's going to happen if I have f of x squared plus 3? That's going to be a quadratic, and what's going to happen to it if I put a +3 on the end? Up 3, right? This is a vertical shift, and we remember that it goes the direction you think it should go, right? CB, what about x minus 5 to the third? That's a cubic. What's going to happen to that cubic? It'll go to the right 5, and anything inside the parentheses goes to the opposite direction, and this is a horizontal. Yes? Is that on there? Maybe I opened the wrong thing. Let me go back to this slide right here. I'll give you a second to get that down since you didn't have the paper, right paper before. Okay, so questions about this? We remember it fairly well from earlier, hopefully. All right, so with trig functions. The same thing is going to happen. So when I have something like f of x equals sine of x plus 1, that's just going to be the sine function shifted up 1 unit. Okay, good. All right. So in a sine function, the midline is going to be the line that passes through the horizontal line that passes through the middle of the function. So, in just the regular sine function, the one you just graphed on that other paper, what is the midline for that graph? What equals 0? Y equals 0. Y equals 0, which is your x-axis. Right, so originally the midline of a function is just that x-axis, y equals 0, that x-axis there. So, a translation up or down is going to move the midline up or down that many units. So a lot of times with trig functions, the question will not ask you for the vertical shift. It'll ask you for the midline of the function. So like up here for this example right here, the midline for this one would be y equals 1. All right, and remember y equals our horizontal lines there. So midline is pretty straightforward to figure out. It's just whatever that vertical shift is. Okay, any questions? All right. Horizontal shifts are going to have a little extra something about them. So if we just have something like this, cosine of x plus pi, this would be the cosine function shifted to the left pi units. So it works the same, shifting left to right. It's going to be different if we have a change in the period. So if there's a stretch or a shrink, it's going to be a little bit different. So for right now, we're just going to write down that a horizontal shift for trig functions is called a phase shift. So in some instances, horizontal shifts are going to work just like we normally see them, where if I put a plus pi, go to the left pi. In some cases, we're going to have to do a little bit more than that, and I'm going to show you that a little bit in a second. Okay, so it's not all there is here. Okay, I don't really know why I made these negative right here. Make them back positive. Negatives reflect things, and we're not going to worry about reflecting right now. Even though they could still be negative. Be fine. Okay, so expansions and compressions were a little bit more difficult than the shifts up, down, left, right. So if I have a 3 on the outside, Paul, what does that do to the graph? Vertical expansion. It's vertical because it's on the outside of the parentheses, or in this case, absolute value bars. It is an expansion because it's on the outside. Big numbers make something bigger. Okay, Cade, what would 0.25 times the absolute value of x do? Vertical compression. Okay, things are backwards when we're on the inside of the parentheses. So, Sarita, what's going to happen for the next one, 2x squared? Good. Horizontal compression. Okay, compression here because a big number, like 2, big number here being any number bigger than 1, is going to actually shrink the graph, right? It's going to make it, or shrink this way. It's going to make it, shorter this way. So we have a horizontal compression. And then, Zach Hawkins, what about the last one? What would that one be? Okay, so it'll be horizontal expansion. Small numbers actually make it larger. So remember going over this stuff. I hope maybe it's a good review if you are a little rusty with it. Mm-hmm. Yeah, it would. If we were doing factors, this would be of 1/2 right here. And then expansion would be of, it'd actually be 2 because it's 1 over 1/2 that for that. And then up here it would just be the same. It would be of a factor of 3. And this would be of a factor of 0.25. Okay. All right, so let's look at what this is for trig functions. Amplitude is the distance from the midline to the maximum point. Or we could say minimum point. It doesn't really matter here. So these are your vertical expansions and compressions here. So if you think about what that trig function looks like, if you have vertical expansion, it's going to make all of those like ridges taller. Right? If you have a compression, it's going to make it shorter. Amplitude is really simple to find with trig functions. Amplitude is your vertical expansion or compression. Also, notice here, I say y equals a sine x, then absolute value of a is the amplitude. Absolute value bars are there because amplitude is always positive. So even if I had like a negative 3 sine x here, the amplitude for that would still be 3. And so the amplitude for y equals 1/2 sine x is 1/2. And the amplitude for 1/30 sine x is 1/30. And this would be the same if those were cosines instead of sines. They all work the same. So amplitude, most students usually feel like is the easiest thing to find from a trig equation. It's just going to be that number in front of your sine or cosine. All right. Horizontal shift. So the period of your function, we really already kind of had this written down. It is the length of the interval over which the function repeats. So it's how long it takes before your function starts repeating again, right? So normally, with just sine or cosine that has not been transformed in any way, the period is going to be 2 pi. But if we have a horizontal expansion or compression, think about what that sine graph looks like. If you take it and pull it out or push it in, it's like an accordion, right? So if you do like this, it's going to stretch it out, and that period is going to be longer. If you squish it in, it's going to make the curves really tight together, and it's going to make them the period smaller. So much like with our factors for our expansions and compressions, because this is inside of the parentheses, it's going to be backwards from what we usually deal with. So normally the period would be 2 pi, but if we have a number in front of our x or our theta or whatever variable we have here, we're going to have to divide by that number. So the period is going to be 2 pi divided by b, or whatever number is in front of your x there. So if we have a number in front of our variable inside of the parentheses, then the period is going to be 2 pi divided by that number. So 2 pi divided by 5. And you see what happens here? Big numbers, like a 5, actually make the period smaller because you're dividing here, right? But if we have small numbers like 1/2, then our period is going to be 2 pi divided by 1/2, which is going to be 2 pi times 2 over 1, which equals 4 pi. So that's a horizontal expansion. That small number actually makes the period larger. Okay, questions? All right, so the trickiest part of this is whenever you have a period and a phase shift at the same time. And possibly one of the reasons it's tricky is because I never made you do it with any of the other functions we've dealt with so far. So I pretty much just didn't give you any problems where you had horizontal expansions and compressions and shifts left and right at the same time. But we can't avoid them with trig because they're going to be really necessary to make equations that work for situations. So we've got to deal with it here. So if your period is not 2 pi, it affects the phase shift as well. So if y equals sine of bx plus c, there is a phase shift of c over b in the opposite direction. Oh. So if I have cosine of 2x plus pi, then first let's do the period for this. So for the period, we're going to do 2 pi divided by that number in front of our x, which is going to be 2. So we would get a period of just pi. For our phase shift, we're going to take this number that's added over here. This is normally the number, like normally we would just say this goes to the left pi, right? But because we got that phase shift, we have to do to the left pi divided by this number in front of your x, which is a 2. So it would be negative pi over 2, or you could say left pi over 2. Yep. If we have one like number, or the second one here, the period for this one is going to be always 2 pi divided by number in front of x, which is 1/3. So that's 2 pi times 3 over 1. And we get 6 pi for our period here. And then our phase shift is going to be this number here and opposite sign. So left 9 over the number in front of our x. So 1/3, which is going to be negative 9 times 3 over 1. So negative 27 there, or left 27. All right, questions? All right, so let's summarize here what's happening, okay? So I've just used the letters A, B, C, and D right here. So A, B, C, and D are all constants that we could replace with numbers. X is my variable here. And then it does not matter whether you're doing sine or cosine. Everything works the same for sine and cosine. The only difference is the graph you start with looks a little bit different, right? So the period for any of these is going to be 2 pi divided by b, the number in front of your x. Your amplitude is always a. And I guess I should put absolute value bars right there. Absolute value bars of a. I was like 2. Stick with my original a there. All right, the midline is going to be y equals d. And that's our vertical shift there. And our phase shift is going to be negative c over b. So this slide right here may be the most helpful whenever you're dealing with these. If we know those 4 pieces of information here, then we can use that to answer any of the questions that we'll see for these. Okay? All right, so let's look at some of these. Now, here is, and actually I want to change my directions a little bit. Instead of vertical shift, let's find midline. One thing you may want to note here is trig, or well, I shouldn't say trig, sine and cosine functions, because tangent is a whole different animal. Sine and cosine always have a period, amplitude, and midline. So even if there's not a number there telling you that there's a shift, there's always a period, amplitude, and midline, right? Because sine, just the main function for sine, has a period of 2 pi, an amplitude of 1, and a midline at y equals 0. So you always have those three things. The only one you may not have is the phase shift. Sometimes there's no phase shift, and that's okay. But you will always have an answer for amplitude, period, and midline. So if we look at this, Wesley, what is my amplitude for number 1? 3. And let's see, Matthew Bashir's, what would my period be for this one?
Wait, no. Sorry. That would be 2 pi over 3.
Not 3. All right, so there are no parentheses in here, but if there were, it would only go around that x right there. Is there, so the number we're looking for period, is that number right in front of our x inside of the parentheses? There's not 1, so it's a 1. So it's 2 pi over 1, which is just 2 pi, right? So there is no change to your period here, but you still have a period. It is 2 pi. Does that make sense? Okay. But what Matthew was doing there is very common. Is like we're trying to do something to it, right? We think it should be different. But if there's no number on the inside of the parentheses in front of that x, then it's just going to be 2 pi. Okay. Ethan, what would the midline be for this one? Good. Y equals 4. That 4 on the end moves this up 4, which is going to take that midline and move it up 4. And I'm just going to put PS for phase shift. What is our phase shift here, anyone? I'm seeing head shaking. No, there is none. So you do not have a phase shift for this one. To have a phase shift, we would have had to have a number added or subtracted to that x on the inside there. Okay, questions? All right, Bo, what's my amplitude for number 2? Good. Lauren, what's my period for the second question? It is 2 pi. Because there is no number in front of that x, which means it's like there's a 1 there. Good. All right. Let's see. Mia, what's the midline? Okay. It normally is just the x-axis, which is 0. So we'll have y equals 0, because this one has not been shifted anywhere. And then, let's see, Zach Darnell, what is my phase shift? Is 3. And that'll be a positive 3 or right 3. And in this case, this is just a pretty straightforward phase shift because your period did not change, right? You could still do 3 over 1, which will give you 3 here. Because for phase shift, we have to take this number and divide it by the number in front of the x. But in this case, there isn't a number in front of the x, so it's just going to be a 3. All right, questions? Okay, let's keep going here. Let's see. CB, what's the amplitude for number 3? Okay. Raven, what's the period? Very good. 2 pi over 2, which is just pi. Very good. Josie, what would the midline be? 0. Y equals 0 here because you're not got anything added to the end. And then, Matthew Pelkey, what would our phase shift be? Okay, perfect. -2. How'd you get that? Very good. And that gives us our -2 there. Okay, questions? All right, Paul, what's the amplitude for number 4? It is 1. Very good. Okay, I'm glad that you got that one. Sometimes students want to put a 0 or something there, but when there's no number out there, it's just a 1. And then, right. Yeah. Think about what number you could put there that wouldn't change anything. So, like, I could put a 1 right here. I could multiply by that 1, and it would not change anything. But over here, if I put +1, that would make a difference, right? But I could put +0, and it wouldn't change anything. Okay, let's see. Manuel, what's my period going to be for number 4? 2 pi over 3. Beautiful. Let's see. Ethan, what's the midline? Very good. And Matthew Bashirs, what's the phase shift? Not 4. It's going to be over 3. Phase shift is going to be on the inside of the parentheses. 6 over 3. And since it's negative, it'll be positive. You'll go in the right direction here, so you'll get just a positive 2 or right 2.
Wait, so is the equation for phase shift C over B?
C over B, yes. Yeah. Okay, questions? Okay, so now we are going to write functions given that we know parts of it. So some of this is super easy, and some of it is a little more difficult, right? So so we have a sine function. So I'm just going to go ahead and say, I know I've got y equals a sine of b. I'm going to use a theta right here, plus c. I'm mostly just using the theta because I haven't used it in the notes yet, and lots of places like to use a theta instead of an x. So it's just a variable like an x. So I'm going to use that theta right here. So treat it like the x. I use x in the notes because thetas are hard to type. You can't just type them in like you can the other. So some of this is pretty easy to fill in. So amplitude is very simple. It just goes right here. So y is going to equal 4 times sine of, we're going to have something in here. Vertical shift is also easy. In this particular case, we don't have one, which means we got 0. It goes over here as your d. So far, we know that we don't have a number here on the end, and we've got a 4 out front. The stuff on the inside is a little bit trickier, but if I have a period of 2 pi, what number has to be in front of my variable? A 1, right? So I just have a theta right there. I can put a 1 if I want. And so if there is no number in front of the theta, phase shifts are no longer complicated. It's just going to be opposite sign plus 2 right here. So this one is not terribly bad because it did not have a period change, which makes it much easier to deal with. But let's look at the second one. It's going to be a lot more difficult because it has a period change. So I know my amplitude is going to be 1/2, so I'm going to have 1/2 out here. Cosine of, right now I'm just going to say b theta plus c. And I've got a vertical shift of 3. So that means I got to put a plus 3 out here on the end. Are we all okay with those? Okay, so those are our easy points on these problems. Usually on a lot of the stuff I'm going to give you, it's going to be on Canvas. It's going to have like 4 blanks that you got to fill in. It's going to look like this. So that first one and last one are the easy ones to fill in. These middle ones are the hard ones to fill in. So if I know I'm going to have a period of pi, what number has to go there for the b? 2. Now, sometimes it's hard to figure that out. This one's pretty simple, but so I know to find the period, I always do 2 pi over b, right? And I want the period to be pi here. Well, it's really easy to see here. That just needs to be 2, so the 2's will cancel and you'll get pi. But sometimes it's not so easy. So if it's not, you can multiply both sides by b. 2 pi equals pi times b. Divide both sides by b, by pi. And you get 2 for your b. That I'm showing you, not because you need to do it on this problem, but because you're going to see some problems where it's not so easy to figure out in your heads. And you might need to just set that up. 2 pi over b, set it equal to the period. All right, if I have a phase shift of c, so I know now that b, let me go ahead and put that in so I know that it is a 2. If I have a phase shift of c, and I know my phase shift is supposed to be 1, what number needs to go there for c? Okay, it needs to be a -2. Sometimes it's not that easy to figure that out in your head. So what you can do, you always want to find b first. I know to find phase shift, I've got to do -c over b, which we found to be 2, right? And that has to equal the phase shift, which is 1. So I can set up that equation, multiply both sides by 2. -c equals 2, divided by -1. C equals -2. So right here, we would have a -2. Okay, questions? All right, so the assignment's not really that's at the end. I don't know if it's on the end of yours. Let me show you what we're going to have for the assignment. It is on Delta Math. Okay, so amplitude midline, this is going to be timed, but that's because they're super fast to do. Okay, so it's going to look like this when you start. You're just going to have to find, like, amplitude of this would be, midline right here looks like it's at -1, amplitude 1, 2, 3, 4. So it's going to be, oh wait, how do we know whether it's sine or cosine? Yeah, sine is going to have a y-intercept originally at 0, so it's going to hit the midline in the middle. This, since it starts at a tall point, is going to be a cosine. So it would be this one right here. So here, midline at -4, amplitude of 1. That's also a cosine because it's a maximum right there. So you'll just go through these here, and I think you have to get, it'll tell you up here your score out of 10. I don't think it stops you when you get to 10 out of 10. So don't do this forever. When you get 10 out of 10, you can stop there. Yes? Huh? That's also part of your practice. But that hopefully should not take any more than 10 minutes to do. And this also should be pretty fast. Here, this is going to be determining the period. So, like, this one's a little tougher than some of the ones that we saw, but it's the same thing. To find the periods, you need this number right here, right? So you would do 2 pi divided by 8 pi over 3. And dividing fractions is easy as pie. Flip the second and multiply. You'll get 6 pi over 8 pi. Pi's cancel. You get 3/4 for that. So some of them may be a little bit more complicated, but it's still that same thing for period. So that should be pretty quick. Then right here, this is going to ask you to write the equation. It is not going to have any phase shifts on it. So, like to look at this one, the period is the most complicated part of this. You have an amplitude of 2. And a midline of 5, so you'll have plus 5 out here on the end. And then on the inside right here, we need a period of 4 over 7. So that was not as easy to come up with off the top of your head, right? But to find the period, we know we always do 2 pi divided by b. And so 2 pi divided by b is supposed to give us, in this case, 4/7. So if we solve that equation for b, we could cross multiply. We would get 4b equals 14 pi and divide by 4. So b would equal 7 pi over 2. That would have probably been hard to come up with off the top of your head. So use this equation method. 2 pi over b equals whatever the period's supposed to be here. So change this, so let me type. So we would type in 2 sine of 7 pi over 2 times x plus 5. So that is what you will do for this part. Right? So amplitude, midline should be pretty straightforward. It's that period part that you're going to have to work for. Let's do this one just to make sure you guys are with me on this. So like for this one, sine function, amplitude is 3. And then the midline is 5. So when we want to find that period, what's the formula for the period? 2 pi over b. We want the period to equal 1/8, so we're going to set that equal to 1/8. You will cross multiply. In this case, you'll get b equals 16 pi. Right, so that is the number that goes right here. Make sure you still leave the x in. So when you type that in, it would do that. But it was y equals 3 sine of 16 pi times x. Make sure you put the x there with it, because I feel like that's something we're going to mess up. Is the pi seems like it's your variable, but it's not. And then we put a plus 5 on the end. Oh, don't put the y equals, because it's already got the f of x equals here. And so that's what you'll do for those last few. Okay, questions? I do not expect for this right here to take you more than 30 minutes. If it is taking you a really long time to do this, you're probably doing something wrong. If you see that it has taken, if you've done a lot of questions and you're getting a lot of them wrong, let's say if you've done, in this section right here, if you've done more than 15 questions and you just keep you're not making any progress, you're still getting them wrong, it is okay to quit if you get stuck on that. But hopefully you will not. Okay, questions? All right, let me get everybody a wipe. We have faculty meeting in the morning, so I did not have smart breakfast, but I will give you a few minutes to ask questions before we take our quiz. study in that unit circle because Thursday happens of it. Oh, it's still recording.